Hello, greetings. Hello and welcome. Today we'll be having a review of basic electrical engineering. First of all, electrical engineering is revolved around electricity. But what is electricity? Well, it's defined here. Electricity is defined as the flow of electric charge. Electricity is also known as electric current. So, electric charge is carried by protons and electrons. It can be either positive or negative. Well, you can see that electrons are an elementary particle, so they would have a negative charge compared to protons, which should have a positive one. Elementary charge is defined as 1.602 times 10 to the negative 19 coulombs. Coulombs is the unit of charge. The elementary charge defined here is the charge of one electron. So, you can see here, the current formula will be I equals to Q over T, where Q is the charge and T is time. So, current literally means the amount of charge per unit time, which is the unit is in coulombs per second. Coulombs being the unit of charge and seconds being the unit of time, which is also known as amperes. I equals Q over T. So there should be a sample problem here. A stun gun delivers 3 amps of peak current in pulses lasting 80 microseconds. One pull of the trigger delivers 95 pulses in a 5-second cycle. Determine the total charge delivered by the stun gun in one cycle. So, as we know, the formula is I equals Q over T. So, by multiplying T on both sides, you would get Q. Q is equal to 3 amps, which is the charge, times 80 microseconds per pulse, which is the time that lasts per pulse, times 95 pulses, which is the number of pulses, times 1 second per 1 million microseconds. That would equate to 0.0228 coulombs, which is the amount of charge delivered by the stun gun. Which does not sound a lot, but considering the astronomically small value of a charge in one electron, that is quite a lot of electrons transferred to the body that is being tased. Hello, and this time we're going to talk about the American wire gauge. The American wire gauge is a logarithmic step standardized wire gauge system used since 1857, mostly in North America. That's why it's called the American wire gauge. The larger number it has means the smaller diameter of the wire. I'm not going to list everything down because it will take too long, but the cross-sectional area of each gauge is an important factor for determining its current carrying capacity. So you see, depending on the cross-sectional area of the wire, it can carry different amounts of current without overheating. So the thicker the wire, the more current it can take before it heating up. So if you pass a large current in a very small wire, it can actually burn the rubber housing, and it could actually glow so hot. It'll actually be so hot that it can glow. An example of this would be the incandescent bulb. It uses a very thin wire that is made out of tungsten, if I remember correctly. And then current is passed through that very thin wire. That's why it brings out light. It actually produces light because it's glowing so hot because so much current is passing through it and it's such a thin wire. The reason why it's not completely burning is because of the inert gas inside the bulb. Oxygen is needed in order for combustion to occur. So if it doesn't have any oxygen, it'll just glow. It won't burn actually. So next one is electrical hazards. As we all know, some feeling electricity can be a pleasant sensation to a fatal one. So the current here is 1 milliamp. 1 milliamp is barely perceptible. You can barely feel it. 1 to 3 milliamps is the perception threshold, which means you can still feel it, but it's about to hurt. It's the peak current that you could feel without experiencing pain, because 3 to 9 milliamps could be painful for most people. 9 to 25 milliamps would cause muscular contraction, meaning if you touch something and it shocks you with 9 to 25 milliamps, you can't let go of it because your muscles are contracting, you're no longer able to control it. And 25 to 60 milliamps is respiratory paralysis, which speaks for itself, it's not good. 60 milliamps or more, ventricular fibrillation. So you see, the heart's rhythm is dictated by the electrical signals and pulses behind it. So getting 60 milliamps or more could lead to it being irregular. The beat would be irregular because of the disruption of the current flowing through it. And 4 amps or more could lead to tissue burning. And anything above 25 milliamps may be fatal if it's under the right circumstances. Hello and welcome. Today we will be talking about resistance and resistivity. Resistance is a measure of opposition to current flow, which means whatever the resistance is, it is the amount of which it restricts the flow of current. The higher the resistance, the lower the current flow, which would make sense because it does oppose, in fact, the current flow. The resistance of an object is dependent on the type of material. Of course, different types of materials have different resistivities. The cross-sectional area of the material, the wire or whatever the medium is, the length of the medium, and the temperature. Leading to the formula R equals rho L over A, which is R is the resistance, rho is the resistivity, L is the length, and A is the area. You can see how some parts of the formula are directly proportional to the resistance, such as resistivity and the length. So the higher the resistivity and the longer it is, the higher the resistance. And yet the area is inversely proportional, which means the higher the area, the lower the resistance. So resistance is measured in ohms, resistivity is measured in ohm meters, the length is in meters, and area is meters squared in the SI units. The sample problem I have here is a 10 meter length of wire with a diameter of 1.5 millimeters is found to have a resistance of 1.56 ohms. What is the resistivity of the wire? So we go back to our formula. R equals rho L over A. Rearrange that a bit, multiply A both sides, RA, divide both sides by L, so that we have rho, which is the resistivity, alone on one side. So you just plug in the values you have. 1.56 is the resistance. You have the area, and you have the diameter. The diameter is 1.5 millimeters, which is 0.0015 meters. So you substitute that in the formula of a circle. The area of a circle is pi d squared over 4. Divided by 10 meters, you would have 2.75 times 10 to the negative 7 ohm meters, which would be the value of your resistivity. Okay, so next up we have conductors and insulators. So I've said earlier that the type of material is quite dependent on the resistance value of the material. So it's classified into two things: conductors and insulators. Conductors are materials that offer very little resistance, where electrons can flow freely, it can move more easily. Example of this would be most metals, but the most prominent ones would be silver, copper, iron, and gold. Silver is actually the best conductor of electricity, though copper is much more widely used because it's just much more abundant and easier to access than silver. Silver is quite it's not really rare, but it's a more common metal than copper, so it's used in more precious applications. And the next one is insulators. Insulators, on the other hand, are materials that present high resistance and restrict the flow of electrons. It mostly has something to do with their structure, with their molecular structure. An example of this would be rubber, paper, glass, wood, and plastic. If you try to force current into them, most likely they will in fact burn because they cannot take the current. So this time we'll be talking about the temperature effect on resistance. I've said earlier that temperature does in fact have an effect on resistance. The resistance of a metal conductor is due to the collisions between the free electrons of the electric current and the metal ions of the wire. If the temperature of the metal conductor increases, the ions of the metal vibrate more vigorously, causing more collisions between the free electrons and the metal ions. Usually, the heat is just generated due to the flow of the current, which increases heat, which in turn increases resistance. So the formula would be R2 is equal to R1 times 1 plus alpha delta T, where R2 is the final resistance, R1 is the initial resistance, alpha is the temperature coefficient of resistance, and delta T is the change in temperature. The sample problem here says a copper wire with an alpha of 0.0068 has a resistance of 26 ohms at 20 degrees Celsius. What will its resistance be at 30 degrees Celsius? So we have the formula here, R2 in ohms, R1 in ohms, 1 plus alpha. Alpha has a unit of 1 over degrees Celsius, or whatever the temperature may be, and delta T is in Celsius. So R2 is equal to 26 ohms times 1 plus 0.068 per degree Celsius times 30 degrees, the final temperature, minus 20 degrees, which is the initial temperature, which brings us to a resistance of 27.068 ohms, which is higher than the initial one because its temperature increases, and when the temperature increases, the resistance also increases. And that's it. So we'll be talking about electron drift velocity this time. So electron drift velocity is the average velocity attained by charged particles in an example is electrons in a material. So it's basically how fast the electrons are moving in a material. An example is a copper wire. So how fast the average speed of the electrons is moving. So it is measured in meters per second. So here's the formula. Vd is equal to the current over NEQ, which Vd is the drift velocity in meters per second. I is the current in amperes, which is equivalent to coulombs per second. N is the free electron density, which is the density of the free electrons. Free electrons is the outermost electrons, also known as the valence electrons. It is measured by the number of electrons per meter cubed. And E is the elementary charge, which is 1.602 times 10 to the negative 19 coulombs per electron, which is also measured in coulombs per electron. And A is the cross-sectional area measured in meters squared. So you can see that the higher the current, the faster the drift velocity is, and the higher anything else, well, most of it is just constant, except for the area. Then it would bring down the drift velocity. Why is it E though? It should be A. Sample problem. Electricity is most commonly conducted through copper wires. Copper has one free electron per atom, so N would be equal to 8.5 times 10 to 28 electrons per meter cube, which would be the free electron density. Assume a current of 1 amp, which is 1 coulomb per second, and a wire diameter of 2 millimeters. So I've calculated the area because it's just a circular wire, so the area would be in meters squared. It would be 3.14 times 10 to the negative 6 meters squared. So here's the formula: VD is equal to I over NAQ. On the top is just 1 ampere, 1 coulomb per second. The bottom is 8.5 times 10 to the 28 electrons per meter cube, which is the free electron density once again. The area 3.14 times 10 to the negative 6 meters squared times multiplied by the elementary charge, the charge of an electron, which is 1.602 times 10 to the negative 19, was it? Yeah, negative 19 coulombs per electron, which would bring you a drift velocity of 2.3 times 10 to the negative 5 meters per second, which is an astronomically small number, which means the velocity is also astronomically small. So it's moving very, very slowly in terms of meters per second. So it may seem that the electrons are moving quite fast in real life, but in reality, they are moving very, very slowly. That's almost unnoticeable to the naked eye. So now we're going to talk about DC circuits and Ohm's law. A DC circuit, which is a closed path in which direct current flows. The current only flows in one direction, which is from negative to positive, since electrons are negative and they would like to go to a positive charge area. But in convention, the flow is going from positive to negative just because of a misconception where they thought it was positive and negative, and so they just lived with it. So it is mostly used in low voltage applications. An example of DC circuit would be here. Here's the cell, the switch which connects and disconnects the circuit, the load, a voltmeter measuring the voltage in parallel, and an ammeter measuring the current in the circuit. So Ohm's law, defined by V equals IR, where V is voltage, I is current, and R is resistance. It shows the relation between voltage, current, and resistance. So voltage, if you don't know, is also called the potential difference, because it shows the difference. It shows the potential difference between 2 points, which means it shows its it shows its driving force, this maximum driving force for the current to flow. So I, which is the current, it's measured in amps, is the electric current, the amount of charge that flows in a certain amount of time, and R is the resistance, which tries to restrict the current from flowing, which is measured in ohms, and V is volts. That's it. So here we have an example of Ohm's law. Ohm's law makes it possible to solve for a known voltage, current, or resistance. So here we have a simple circuit which has a 30 volt battery source, or potential difference as you may call it, and with a single 75 ohm resistor, and we don't know the current, so we're going to use Ohm's law, which is V equals IR. So for I is I equals VR. So substitute the values, 30 volts over 75 ohms, then you will get a current, total current of 0.4 amps across the circuit. And for our final topic, it's the series and the parallel circuit. So the series and parallel circuits are two types of DC circuits that have different properties, and we'll show you. In a series circuit, there's only one path to current, so the current is the same everywhere in the circuit. So whichever point you measure it with an ammeter, you will always get the same current. So let's see here, let's solve one. With the battery cell of 30 volts, there are 100 ohm, there is a 100 ohm resistor plus, and a 50 ohm resistor in series. So the equivalent resistance of that would be R1 plus R2 plus R3. Just add them all together. So the equivalent resistance would be 100 plus 50, which would be equal to 150 ohms. So using Ohm's law, we'll solve for the current. So I is equal to V over R equivalent, which would be 30 volts over 150 ohms, which would equate to 0.2 amps. So for a parallel circuit, all resistors share a common voltage, but currents to each depend on the values of each resistor. So the equivalent resistance would be 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so on. Sorry, this should be 1 over R equal 1 over R equivalent. So R equivalent in this circuit, there's a 30 volt battery, and if you go around here, there are two resistors in parallel. So these two are in parallel, so their equivalent resistance would be equal to this. So you need to find the current all throughout the circuit. So in order to do that, you would need to make these two parallel resistors into a series. So by doing that, you would get R equivalent is equal to 1 over 150, which is the value of the first resistor, plus 1 over 100, which is the value of the second resistor. So if you combine those together, you would get 60 ohms as an equivalent resistance in one single resistor. So if you substitute that single resistor here, you would get a series. So using Ohm's law once again, you will use that to calculate the current throughout the circuit. So I is equal to 30 volts over R equivalent. In this case, our R equivalent is 60 ohms. So 30 volts divided by 60 ohms, you will get 0.5 amperes in the whole circuit. But if you were to find the current in each of the resistors, you would need to substitute the resistors. You need to substitute the R equivalent into the value of the resistor in the parallel. So using Ohm's law once again, V equals IR. V is 30 volts divided by R for this current. This resistor right here is 150. 30 divided by 150 would be equal to 0.2 amps. So in this case, here's another one. 30 over 100 ohms is the other resistor. 30 over 100 would be equal to 0.3, which is also in amps. The two resistors in parallel, the current flowing through one another should always equal the total current in series. And that's it.